Okay, I think we're going to go ahead and get started. Greetings, everybody. Welcome to our OSIRIS-REx live stream event. My name is Mike Murray. I'm with the Delta College Planetarium in Bay City, Michigan, and we're going to explore a very historic event that just took place a few weeks ago, the largest sample ever gathered from the surface of an asteroid that will be returned to Earth. It's an asteroid sample return mission, as NASA likes to put it. And what we'd like to do now is let's describe, first of all, a little bit of background on the mission. What does this whole OSIRIS-REx thing even mean? Now, as you might know, NASA loves acronyms, and they also like to find acronyms that are accurate to what the mission is supposed to be portraying. So OSIRIS-REx actually stands for Origins Spectral Interpretation Resource Identification Security Regolith Explorer. Did you get all that? Basically, what we're talking about is being able to examine a pristine asteroid, one that has been very unaltered since the birth of the solar system. We want to be able to identify the minerals, especially something that's got a lot of carbon in it. And regolith refers to the soil, to the surface soil, being able to see just how solid and how secure is this material to the surface. So there's a lot of things that NASA is really looking forward to discovering, but there's a lot of reasons for a mission like this. The purpose really is to try to learn more about near-Earth asteroids. There are hundreds of thousands, if not millions, of asteroids. Most of them we know are between the orbits of Mars and Jupiter. But near-Earth asteroids are those that can cross the orbit of Earth, those that can get closer to the sun, in fact, than the Earth, and can potentially pose a hazard to Earth in terms of collisions. But a lot of the reason we want to be able to study these near-Earth asteroids too is because it gives us a window into the early formation and evolution of the solar system. It helps to tell us a lot more about what conditions were like, and in fact, what conditions were like when the Earth was being born. And so it also helps us to understand a little bit more about how the orbits of these near-Earth asteroids can change over time, because they do have the potential to alter their orbits somewhat from time to time. All right, so why Bennu? How did we come across this particular asteroid as the one that we wanted to encounter and discover and work on? As I was mentioning, there are at least 500,000 asteroids, probably a lot more. We needed an asteroid that would be in that classification of near Earth, to study the hazard likelihood, but also to be able to find the right kind of asteroid that we needed, that would be easy for us to be able to get to. An optimal orbit for sample return means an asteroid that gets close enough to Earth that it wouldn't take a long time or a lot of energy to get there and back. We also wanted an asteroid that would be very small in diameter, about 200 meters or less. That's like about 600 feet across. Low gravity means that it would be very easy for us to approach, to maneuver around, to land and escape. And then finally, we wanted an asteroid that would be very rich in carbon, because that's going to be an important element in terms of helping us to understand more about the history of the solar system and whether or not carbon on the Earth came from asteroids. So we ended up, after years of looking at candidates, with an asteroid called Bennu. So what is it about Bennu? Well, it does turn out to be a carbon type, a type B asteroid, which means that it has a very high carbon and also other minerals that would be very ancient, very easy, and very interesting to look at. It does follow an orbit that's very, very similar to the Earth's, even very similar in inclination, or angle. And it is very, very small. So it's something that fits very nicely. And as you can see, it's a very small size, only about 500 meters across, compared to the other asteroids that we've visited. For reference, 500 meters a little over 1,500 feet. That's not much taller than the Empire State Building. So small is good. Remember, low gravity and being able to have a good loose soil. So what about the spacecraft OSIRIS-REx? What are we looking at here? It's not just going with cameras. It's not going with a shovel to land and scoop up. It's using some very ingenious methods for being able to look at the composition and the mineralogy of the asteroid. So it has a whole entire suite of many different cameras. It has what's called a laser altimeter. This is what will bounce laser beams off the surface to allow us to get 3D maps of the surface. Helps to identify good landing zones. We have these things called spectrometers. That's a way of looking at the light so that we can see what kind of composition is there. We can look at spectral lines to see, what elements are visible. And so we do use visible light, infrared, IR, meaning infrared, and even thermal in order to help understand a lot more about the composition of the asteroid. And then there's this thing called the touch and go sample system. We'll take a look at that in just a second, but here's a good look at the spacecraft when it was being completed at the Jet Propulsion Laboratory. And as you can see, it's about the size of a minivan, maybe a little larger. This is the antenna that's covered up, and this is the return capsule. This is where the sample will be placed and will actually return to Earth just a few years from now. The spacecraft actually has 28 rocket engines on it. And this is for flight path adjustments, for orbital changes, and thrusters for the touch and go operation. So it's pretty complex. Finally here, let's get to this arm that you saw sticking out of the spacecraft. They call it the taxam because the way that they're going to sample the surface is not to actually land and try to scoop anything up like we did in the old days on the moon. It's more like a touch and go system where this disk will actually only touch the surface for about 5 seconds and pull up material inside of it. So how's it going to do that? Well, the taxam is kind of like an air filter. It uses high pressure nitrogen gas to agitate the soil and pushing some of it into the collector. And so you see how it's got a little opening at the bottom. To give you a little better idea, let's look at this animation of what is supposed to happen. The spacecraft will come down at a very, very slow rate. That will allow the disk to touch the surface. Nitrogen gas forces down into the soil, loosens it up, and pushes some of it through a flap that will end up all around the edges of the chamber. And so it's hoping to be able to find a significant amount of sample, more than we've ever been able to collect from any other surface other than the moon. And so this is going to be a very ingenious way of being able to get the material off the surface. Again, we wanted a small asteroid because the surface would be very loose and a lot easier to gather the material. So with all of that, years of study, years of engineering and design, OSIRIS-REx was launched on an Atlas V rocket back in September of 2016. The rocket, of course, had an upper stage which put it on a trajectory actually around the sun to begin with. The spacecraft orbited around the sun for about a year and then actually came back to the Earth first. It needed to pass underneath the south pole of the Earth, underneath Antarctica, in order to get what's called a gravity assist. It needed to be able to adjust its velocity and its angle. It even looked at the Earth and the moon to test its instruments. But see, what happened is it needed to be able to match the angle, match the trajectory, and also speed on an intercept course. So it was about late in 2018 when OSIRIS-REx was finally able to see Bennu as just a dot. Over the coming months, it grew and grew into a little world. We were able to see a little bit more of its size, its shape, and even its rotation. By December of 2018, we were able to actually start to see a little bit more than just a tiny sphere. Actually, it's more like a diamond shape, which is typical for asteroids this small. They're loose and as they spin. This is a shape that nature likes to make. Now, its approach happened in stages so that the OSIRIS-REx spacecraft would fly kind of in tandem and then move into various positions around the asteroid in order to get different angles for its photographs and to begin its analysis. What we did find, this was the step where it would actually try to establish an orbit. And this is something that's very, very hard, very complicated to do. Orbiting a planet is actually easier because it's got so much mass. Trying to orbit something as small as this tiny 500-meter wide asteroid is very complicated. But once they did establish the orbit, they were able to begin the mapping and the studies with the spectrometers. But there was an immediate issue. When they looked at Bennu, they were expecting and hoping for it to be rather smooth. They were hoping that it would be kind of a sandy surface because that's what some of the infrared studies showed. Other spacecraft and observatories indicated that the way the temperature radiated and cooled from the asteroid as it rotated, they thought it would be smooth. Well, I don't know about you, but it doesn't look too smooth there. Let's take a look at a slow rotation made from thousands of photographs, and laser altimetry as well as the photos showed a world covered with rocks and boulders. In fact, it's hard to find any smooth areas at all. So this was an immediate concern because the taxam is going to need a very smooth, sandy-like surface in order to get a good amount of sample. And over time, and over the next year, they would put OSIRIS-REx down close to the surface so they could get some really high detailed images. And it seemed like almost everywhere you looked, you just had boulders upon boulders and rocks and pebbles, kind of like a loose gravel pit. They did find that it was loose, that the gravity was very sparse, what you'd expect, but it was really hard to find anything smooth. They did occasionally find some unusual looking rocks like this heart rock, which is evidence that there are other asteroids that have deposited rocks onto its surface. But it seemed like everywhere you looked, rubble pile. So it took many months. In fact, it took over a year of studying the surface in very high detail to find 4 very small candidate sites with the right surface as well as the right chemistry for where they would want to take a sample. They ended up in a spot here called Nightingale Crater. Ideally, they would want a space with about 50 meters wide. That's like over 150 feet, 160 feet. Well, Nightingale only gave them about 26 feet. So it was going to be a very, very tight target. In fact, what they needed to do was program the spacecraft to look and identify like some very bright rocks, which would be used as navigation point sources so that they would be able to get an even tighter spot when they went to land or touch and go, I should say. So you got to remember that the spacecraft is 200 million miles away when it's doing this, so it all has to be automated. There's not somebody back here on Earth with a joystick that's making it happen in real time. This all had to be programmed very detailed ahead of time. And you have things like the heat coming off of the surface, you had the solar radiation on the spacecraft, all of that had to be taken into account because it could alter the position of the spacecraft. So finally, the first date was set for the first collection attempt. It had enough nitrogen gas to do 3 touch and goes if necessary. The first one was scheduled for just a few weeks ago. And you might have heard a little bit of news about how this went, but look, we're going to recount it for you and give you some great photos and video of what happened. So back on October 20th, OSIRIS-REx fired its thrusters to basically fall out of its parking orbit and then drop down to the surface. And it had to match the rotation rate, here of the asteroid, so that when it came down and tagged, it wasn't moving translationally. 5 or 6 seconds of tag and then thrusters to push it right back off the surface. So how did it go? Let's see. Boosh! Look at all of that debris flying off. In fact, that was incredible. They ended up with a lot more debris being pushed around than they had originally expected. In fact, let's watch that again. When you see all that flying, it's not that it's impacting it so much as it's the nitrogen gas that's pushing down into the soil. In fact, they found that the rubble was so much more loose than they had expected, that they got a lot deeper into the soil and stirred up a lot more of the rocks and pebbles and soil than they expected. So what did that mean for actually being able to collect enough sample? They needed at least 60 grams in order to be able to say it was a successful sample. What the spacecraft would do was push off into a distance away so that it would leave the arm extended. It would leave the arm extended over here and then do a spin maneuver, measure the inertia of the spacecraft, and that way they could use physics to calculate how much sample they had. Well, immediately though, they noticed a problem. There's a camera that actually is specific for looking at the sample. And this is what it saw. Did you see that? Debris was actually leaking out of the sample disk. Apparently, it was too successful. What happened? They had so much rocks and pebbles and debris that it blocked the mylar flap from closing back in and sealing the sample inside around the edge of the disk. So they didn't want to risk doing the spin maneuver in order to measure how much sample they had. They needed to try and get that sample stowed away as quickly as possible. And so what they would do is open up the return capsule. They would put the sample disk back down, lock it into place, and the arm would come off and the lid would come back down and seal the capsule. That's the only part that would return to Earth. So they weren't sure exactly how much sample they got. They're pretty confident that they got way more than they needed. Some estimates put it as high as 2.5 kilograms. Well, that's about 7 pounds of material. That's thousands of times more than has ever been gathered from an asteroid before. The Japanese space agency Hayabusa visited an asteroid and returned only some small, tiny grains half the width of the human hair. This is amazing if they're going to be able to get what they think they got, 2.5 kilograms or so. Okay, so what does that mean? Does that mean that OSIRIS is immediately heading back to Earth? Well, it can't. We need the orbits of Bennu and the Earth in order to get to the right positions before Bennu can leave for its return course. So it still has a few months that it's going to stay in orbit. It'll be continuing to orbit to map even further. It'll look at the sample site. One of the things we did notice almost right away was how loose the rubble is on Bennu. It turns out that there might even be some tiny voids inside of Bennu. That led to a sensational headline that came out in Business Insider a couple of weeks ago, implying that is Bennu hollow inside? Well, not exactly. It is very loose, and there might be some voids in various parts inside, but it's not hollow in the sense that it would be like only material around the edge. The fact that Bennu rotates in only 4 hours means that it's spinning at a pretty good rate. And with something that tiny, it's going to actually literally spin some material right off the surface. Some of it will fall back on, some of it will escape. Turns out some of these are anywhere between the size of a pebble and a 4-inch rock. And even with that small size, Bennu may spin itself out in about 1 million years. But it's not hollow like some of the headlines led it to believe. So when will OSIRIS-REx leave Bennu? It'll be a few months. So in the month of March is when the alignment will be just right. The rockets will fire. This is a nice photograph of Earth and Moon taken from Bennu. And so it'll be getting, it has a very good camera, as you can see, a narrow field camera. And let's take a look at the return journey here for a moment. OSIRIS-REx has to get lined up. It will cross the path of Earth. The spacecraft itself, the whole spacecraft is not coming down into Earth at all, but the capsule will be released at just the right moment, at just the right angle. It'll re-enter the Earth's atmosphere, and it's due to touch down in the Utah desert. There's the Great Salt Lake City. It's coming down in an area called the Dugway Research Range, the Utah Test Range. The Genesis spacecraft some years ago made a landing there, so we've done this before. As soon as it's recovered, it'll be isolated, and it will be sent to the receiving lab at the Johnson Space Flight Center in Houston. And there will be our first opportunity to see just how much sample we really gathered. A very exciting time. We've never been able to use a technique like this. There's so much scientists have learned, and hopefully there's going to be a lot more to learn about the sample, because this is the most pristine, unaltered material from the earliest days of the solar system. It's probably from less than 100 million years after the solar system formed, over 4.5 billion years ago. So this is a really unique opportunity, because we don't find anything like this on the Earth, because the Earth, of course, has an atmosphere, and it has volcanoes and tectonic movement. And so almost all of the oldest material on the Earth has been erased or reformed. So this is going to be an exciting time. In fact, for years, they'll be studying these samples to see what kind of carbon it has, and whether or not that carbon is what seeded the Earth for life. Because the earliest days of life on Earth, or the earliest days of the formation of the Earth, I should say, before life got started, the Earth was still molten. It was so hot that the carbon vaporized off into space. And so we had to get our carbon for the development of life from somewhere. And it seems very likely that it came from these carbonaceous asteroids. So this will be helping us to determine if that is indeed the case. But it's why we explore, and it tells us as much about ourselves as about what it is that we're exploring. And so I want to thank you all for attending. Let me